shear stress in beams. Okay? First, let us see what is this shear stress in the beam. Now here I have considered a beam, horizontal beam, which is subjected to pure bending moment, right? When we discussed about shear force diagram and bending moment diagram, uh, we discussed that whenever there is a couple or a bending moment that is applied on the beam and there are no load, then there will be no shear force acting on the beam, right? So that is what I am saying here. When a beam is subjected to constant bending moment, the shear force in the beam is zero, and also the shear stress is zero because shear stress is force by area, and that will also be zero. But in actual practice, the beam is actually subjected to bending moment which varies from point to point. Though we say it is a constant bending moment, the actual bending moment at every point will be different. It will not be same, right? So as a result of this, the shear force acting is also not zero, and it varies from section to section, resulting in shear stress. Since there is shear force, there will be also shear stress which is induced. This shear stress will be acting across transverse section of the beam. Transfer means perpendicular sections, right? So perpendicular sections or transverse sections of the beam. The transverse shear stress produces complementary horizontal shear forces, right? So these transverse shear stress which are perpendicular, they also produces a a complementary horizontal shear force, and these act on the longitudinal layers of the beam. So along the layers of the beam, there will be shear stress which is produced. So that is what we are going to calculate in this particular section, okay, for various cross sections. So we are doing a simple derivation now to find a relation between the shear stress produced and or how to calculate the shear stress produced when we know the shear force. Okay, so I have considered a rectangular cross section beam here, which is simply supported at its ends, and there is a UDL, uniformly distributed load, applied on the beam, right? So because of which there is a constant bending moment on this. Now in this beam, I am considering two sections, AB and CD. Okay, I am enlarging this particular section. So this is AB and this is CD section. These two sections are apart by a distance dx, and because of this load on the beam, there is a bending moment applied. On the left side, the bending moment is m, and on the right side, the bending moment is m plus dm, right? And this is the neutral axis. Now I'm considering a line above the neutral axis, right? I need to find the shear stress in this particular section. Now in this section, I'm considering a small element on which on the section AB, on this section, the stress, bending stress, that is above the neutral axis, it will be compressive. So the compressive stress is equal to sigma here, and on the right hand side, that is on section CD, the stress will be compressive again, and the magnitude is sigma plus d sigma. Okay, now I am further taking this particular cross section, this from AB to CD, this section, I am slicing it and I am tilting it now. So the width of this beam is B, this is the depth of the beam, and this is the dx, this dx. So this is A, B, this is C and D, right? I have just cut and I have rotated like this. Now here, this is the section I have taken. I missed putting marking EF there. So this is represented as EFGH. So I need to find the shear stress at this section EF. Okay. So for doing this, there are different methods that are suggested in the book. This one, what I'm teaching now, is very simple. That's why I'm taking this. So what I do is I'm considering a small elemental cylinder in this particular volume EFGH into dx. So it is a cuboid in which there are infinite number of small cylinders. So out of that I am considering a small cylinder here, one small cylinder. Now this cylinder, the center of this cylinder is at a distance of y from the neutral axis. This is my neutral axis. So it is at a distance of y. And on this cylinder, because of this compressive stress, there is a force, compressive force, which is equal to sigma. Sigma is my compressive stress into dA. dA is the cross-sectional area of this small cylinder. This is dA, and entire area of this EFGH is capital A, right? So sigma into dA will be the force, compressive force on this side of the cylindrical element, and on the opposite side it will be sigma plus d sigma into dA, right? Now with this, let us try to derive the equation. Now let at section AB, F is equal to shear force and B is equal to bending moment. At CD, that is at this section, F plus dF will be the shear force and M plus dM will be the bending moment. Okay, and I is moment of inertia about neutral axis. So I is for the entire cross section, it is not for this particular section, it is for entire cross section, complete cross section. What is the moment of inertia I have calculated, that is I. For cylindrical element in the section that is considered here, dA is the area of elemental cylinder, right? This area is dA. Dx is the length of the cylinder, that is length of this particular element, and y is the distance of elemental cylinder from neutral axis. This I have explained. Now the bending stress sigma here is given by my by I at section AB. Similarly at section CD, the bending stress is sigma plus d sigma, and that is given by M plus dm into y by I. See, y and I will remain same, that will not change. Only the bending moment and the stress value is changing between AB and CD. Now the force on the element on section AB here, this force is sigma into dA, right? Stress into area of element. So that is sigma into dA, and sigma I have calculated earlier as my by I. So my by I into dA gives me the force on element on section AB. Similarly on section CD it will be M plus dm y by I into dA, right? Now by looking at this, I can easily say that there is some unbalanced force. You see this, there is sigma here, there is sigma plus d sigma. Here it is sigma dA, here it is sigma plus d sigma into dA. So there is some unbalanced force, right? So these two forces are acting on the same line. They are acting on the same line, but they are opposite. That is why it is compressive force, right? They are in opposite direction. Since there is difference in these two forces, there will be some unbalanced force which is given by m plus dm y by I into dA minus my by I into dA. So when you expand this m and the m here, that gets cancelled, and what remains is dm by I into y into dA, right? Now this is the unbalanced force on this small element. Now I need to find the unbalanced force on this entire cross section EFGH, right? So the total unbalanced force you can find by integrating the equation dm by I into y into dA, right? dm by I is a constant, so I'll take that out. So integration of y into dA. We have studied this earlier uh, when we discussed about the centroid or center of gravity. Sigma y bar is equal to sigma y uh, into dA by A, right? So that is equal, that is actually y bar, or integration of y into dA will be y bar into A, right? So this part, integration of y into dA in this expression, I am replacing by y bar into A. Why y bar is the distance of CG of area A from the neutral axis. See, y bar is not distance of CG of the entire cross section, it is for this particular section which I have considered, EFGH. Therefore, total unbalanced force is equal to dm by I into y bar A, right? Now this unbalanced force results in shearing of the beam along the section passing through EF. That is, along this section the beam will shear, right? The material of the beam offers shear resistance which should be at least equal to the unbalanced force, right? Shear force tau is equal to force is equal to tau into b into dx, right? Which is equal to dm by I into y bar into a, or tau is equal to dm by dx into a y bar by ib. Now this dm by dx is nothing but your shear force acting in that particular section. So shear force into ay by ib, right? So this is how the shearing takes place. You just see this. I'll do it again. See, because of this force, the section EFGH, whatever is there, along this plane, EF plane, the beam will get sheared if the shear resistance is not strong enough, right? So this particular equation, right, tau is equal to F into AY by IB is what we'll be using for our calculations.